we're going to learn about complexity for the quiz. And we'll learn about MP, whatever, reductions, and this shit. Alright? So first, we will start with decision problems. So what is a decision problem?
Should I drop the course or not?
That is a decision problem.
Yes. Now, is that like P, MP, or MP hard?
It's P.
No, it's MP hard because we don't know if we're going to drop the course.
Oh crap.
Alright, that was bad. No more of that shit. Alright. Decision problem is just that given input x, right? If we input x into the decision problem D, so let x be equal to the input, and D is equal to decision problem, then the output is either yes or no. So given any input for a decision problem, the output is either yes or no. So one example is, can anyone give an example?
Is a number in a list.
Yeah, exactly, is a number in a list. So do you know the difference? So an optimization problem is that, for example, an optimization problem is given a graph, a network, what is the max flow, right? So how do we turn, but here for these complexity classes, we're only going to focus on decision problems. So how do we, you guys know how to convert optimization problem to decision problem? I don't need to go over that.
No. Yeah, you do.
Okay, real quick. So, for example, how do I turn network flow into a decision problem? So network flow is, network flow, the optimization problem is we want the max flow given the network N, right? So in the optimization problem is you want the max flow given the network N, right? So how can we turn that into a decision problem?
Because there exists a max flow?
Does there exist a max flow? Not almost. So this is
Given a flow, is it a max flow?
yes. No, given a no, that's still okay.
Yeah.
Yeah. So for example, given f is it max, right? That's optimization. That is decision, right? So we took the same optimization problem, which is we want to find the max flow f given the network. So given f and n, right? So it's f and n. Is f a max flow, right? So that's how we convert decision problems, optimization problems into decision problems. And we're only going to focus on decision problems for, I guess, the quiz. So there's some notation. So if x is the input and d is the decision problem, we say that x is an element of d if given x, the answer is yes. And then likewise, if x is not an element of d, if given x, answer equals no. Right? So that's just notation, right? Just keep in mind so that you know what exactly this means. Right? So now let's move on to the class of NP. Or first, I guess class P, but that's obvious, right? You guys know what class P is. Solvable in polynomial time. So you guys know what that means, right? So if a problem D, decision problem D is in class P if it is solvable in polynomial time, right? It's pretty straightforward, but one caveat that I'll mention is that, for example, given the problem, we have to focus on, when we say polynomial time, that means that the problem has to be solvable in O of n k, right? Where k is a constant, n is the input. But we have to be careful of what this n means, right? So n has to be the size of the input, so not the actual value. For example, let's say given this problem, huh?
Like let's say given like find the max integer numbers. Like how would you define?
So, like in that case, n, we have to encode the problem in some sort of bits. Okay, hold on. Let me give another example. So let's say that we wanted to do, given n, is there j and k which are also ints? Given n, can we find j and k such that j, k equals n, right? Basically, given n, is n prime or not? This is the question, right? So, in your first intuition, you might think it's linear time, right? Because all you do is just check all the numbers from 1 to n, and then if it divides into n, then we found the answer, right? And you only have to check over n number of times, right? But I guess what they say is that n is not the actual value, but we have to represent the input as a string of bits. So for example, if n is equal to like 4, then the number of bits is 1 and 1. I think, no, it's 1, 0, 1, 0, right? So the input is dependent. If n is the actual value, then the input is dependent on log 2 of n, right? And since n is equal to 2 to the log 2 of n, then if the size of the input, size is equal to log 2n,
Plus 1, right?
yeah, plus 1. So like that, right? Then that means
log of 2n all plus 1, I think.
all plus 1?
Yeah.
Alright, thanks.
That's not it.
Thanks, bro.
So if the size is log 2n plus 1, and we know that n is equal to 2 to the log n, and the problem is O of 2 to the size. So it's actually exponential time.
Just
So this problem of whether the number is prime or not is actually exponential time and not polynomial time. Do you guys kind of get it? To be honest, I don't really get it that much either, but
yeah, move
the
your head.
point is that
Yeah, Amir, move your head.
sometimes,
The size is the size of n, or
so the size is how much, because for any input,
Yeah.
we need to represent the input as a string of bits, right? So you have some sort of, so we have again, some sort of x and d, right? Decision problem is the problem, x is the input, x has to be represented as some string of bits, right? So if we're dealing with this number,
Just put a magnet on. And I think the main idea there is that instead of seeing n equal to 2 to the power log n, just see is equal to k equal to 2 to the power log n. So if we assume, not k, like any digit like L. So if we assume the inputs are n number of inputs, then the amount of calculation we need to do is k equal to 2 to the power that input.
yeah, exactly.
So
it's like the actual size of the bit level.
Yeah, the bit level.
yeah.
I think, to be honest, I don't even really get it. So, well, I just wanted to point that out in case, like, she straight up just says, is prime a polynomial or not? Just say no. Honestly, that's all I really know about this topic. But I don't think we'll get asked on it, so that's just what I wanted to point out. So, is prime
If you want to check the numbers.
is prime is not in P. I think that's just remember that, all right? Or also, if you also have, for example, again, I don't really truly, it's one thing I don't truly understand, but there's also something called pseudo-polynomial. So if it's pseudo-polynomial, it's not actually polynomial. For example,
One
The
more for
knapsack
spelling it
problem.
right.
the knapsack problem, if you guys remember, do you guys remember what the knapsack problem was?
Yeah.
So basically you're given a knapsack which can hold up to a capacity, a weight W, and you want the most amount of items inside. And each item has a weight and a value, and you want to stuff your backpack with as much value as possible while staying under this weight W, right? So basically, if there are n weight is the weight of the backpack, and n equals number of items, then we know that this thing is solvable in O of W times N time, right? Or even theta, actually, to be more precise. But this is not actually polynomial time, it's pseudo-polynomial time. Because it has to be, you can't have some sort of, it has to be only a function of n. There can't be other constants not n, that aren't n. So that's what I wanted to point out too. But if you don't get it, whatever, I don't really get it either. Let's move on. So, let's do, what is NP? First of all, what does NP stand for?
Not
Non-deterministic.
deterministic.
Yeah, make sure it's not non-polynomial, it's non-deterministic. So what is NP?
Non-deterministic.
Alright, what is the class?
Verifiable.
Yeah. So NP is the set of problems so that
Wait, why is this super?
Because the weight is variable.
Well, we can also see that like this is
Because
it's larger than
W can be a lot larger than N,
than W squared.
but N can be a lot larger than W too.
But it doesn't matter, because
And
either one of them
denominator.
are,
It's
Yeah,
so,
so then-
So
that
it's
will-
not actually, it
still
could,
not-
it could be, this could be, what he's saying is,
oh,
but it.
What if W is
instead of being
exponential?
square root.
yeah, like, what if
It
it's
is not.
exponentially related or something?
you guys have any questions?
Yeah, why is that pseudo-polynomial again, like just?
Basically you can only have functions of n. Okay, basically the reason why is because precisely that W is actually a function of the input n. That's why it's not that's not why it's polynomial. So W isn't just an arbitrary constant. It's some function of n.
Oh. Okay.
So
okay.
just know that knapsack is not polynomial. That's it. It's not in P.
W is a
lectures?
function of, W is a function of
Where is
n
this
because as
I think it
you
was
have more
there.
items, the weight of the backpack increases.
Look up pseudo.
I honestly, I
think it
should,
was pseudo.
I don't even know what the hell this means.
I know, I
should
think,
talk about
I know for some sort of
I remember she
complexity,
talked
like,
about knapsacks on
it needs to be like all in terms of like, for a polynomial time, you need to have n to the k, where k is independent of n.
Exactly, right?
So
To be honest, I'm not sure. You're gonna have to look this up. I tried looking it up. It didn't make sense to me. So that's your homework. Just know, whatever. She asks you. I just wanted to point this out. I don't get it, but she asks you, is knapsack
It's pseudo-polynomial.
can be solvable? They give you an algorithm. They say this is the complexity. Is it in polynomial time? Just say no, right? And that's it. And if you don't know why, I don't really know why. Just say W is some function of the input, whatever.
Okay, dumb question. Could it be any under any condition? Could it be polynomial, or is it always pseudo
What
polynomial?
if W is
It's
just
always
a constant?
No, it's always pseudo polynomial. Stop asking questions, okay? The point is that, okay, if we go back to, the point is that that knapsack is an NP problem. If it wasn't polynomial, then we would solve P is NP. We're getting ahead of ourselves. Let's just ignore that, okay? I don't even get that either. Alright, so do you guys know what NP is? Verifiable in polynomial time. So basically, the problem is NP if you can be verified in polynomial time. So for example, the satisfiability problem, you guys know what that is, right? So given some formula f, right, if you have some function Right, so basically, satisfiability means that given some formula, is there some combination of Boolean variables x1, 2, 3, and 4 that will make this formula true, right? So in this case, how would you verify it? Like so basically what verifiable in polynomial time means is that you have an algorithm V which takes in X and C, right? C is the certificate. So the certificate is proof that the problem can be solved.
So
Okay, hold on.
is the certificate just like a solution? Like you'll
Yeah, I think so.
Hold on. Okay. Problems that can be verified. Okay, let me be problems. Sorry, she wrote this. And all problems that this is the important part, whose yes instances can be verified. Can be verified in P. So, what do I mean by yes instances? So again, back to this problem, right? Do you guys know? So if I write it like this, you guys know which that's OR, right? OR is the down hat. This guy here
Not.
is the not, and let's say that this is x4, and then x4 is not. So this is not. This is the up hat is and. The down hat is, so up is and, down is or, and this rectangle thingy is not, right?
Yeah.
So what I mean by the whose yes instance is that if the solution is yes, I can verify that the solution is yes in polynomial time, right? And what I mean by verify is that we need some sort of certificate which proves that this problem can be solved, which proves that this problem can be solved, right? So it's just an example which proves that this problem can be solved. Given the certificate and the input, we can verify it's true in polynomial time. So certificate is just an example, right? For the yes instances. So, for example, so here, what would be a certificate?
1, 1, 0.
So C with the certificate would be x1 is 1, x2 is, so this guy
It could be anything, right?
x2 needs to be 0, x3 needs to be 1, x4 can be whatever. And that's our certificate. So basically so what we mean by verifiable is that given some sort of input and the certificate, which is proof that the thing actually outputs yes, you can verify that it does output
The
yes.
input is the problem, right? Aren't you supposed to give the verifier the problem?
Huh?
Didn't you say
Yeah,
that?
you're giving the verifier the problem, which is this guy. This guy is the x.
So that should be F, right?
Huh?
Where you put X.
No. So F is just like the formula. Don't worry about F, it's for sure. That's our X, right? X is the input, C is the certificate.
Yeah.
And basically it's proof, the certificate is proof that the thing actually outputs yes. The thing where if you plug in the certificate, so the polynomial, the verifier can be run in polynomial time, because all you have to do is plug in the certificate, right?
Yeah.
Now, and why do I say yes instances, right? Because what if the answer was no, right? How would you prove that the answer is no?
Plug
In-
in.
So, like, what certificate could you
You'd
give?
have to know all the solutions to the formula.
Exactly, right? It's easy to say that if the answer was yes, it's easy to prove, right? You just give an example. If the answer is no, how do you prove that? You gotta check all of them, right?
So do we input the certificate into the verifier, or is it the output?
So we input the certificate in the verifier. And in this case, the verifier just takes the certificate and plugs it in and checks if the output is 1.
So the verifier output is either yes or no.
No, yeah.
But how would it ever output no?
I mean, in this case, it could output no, right? Like,
How?
If a certificate,
It would output yes or I don't know, right?
No, but okay, so for example, so it's trying to verify if the certificate actually proves the problem. So for example, if I give you a wrong certificate, the verifier can say, no, this is the wrong certificate. So yeah, if the verifier outputs no, it's saying the certificate is false. You gotta give me another one, right? That's what it means.
Then what's the purpose of X here?
X is just the input.
It's the improper
If it confuses you, just say whatever, ignore it. It's just
Problem?
this guy,
Like the
X,
function
X is,
itself?
X is, yeah, X is the input. C is the
Okay,
certificate.
So let's say I give it an invalid example, right?
Then the verifier will output no, meaning that, but the point, the verifier will output no.
Then why is only yes instances?
Right, so it's only yes instances because how can I prove the answer is yes here? You just give an example, right?
Yeah.
Which is certificate. doesn't
Which is a
it?
certificate. How do I prove this is no, this is wrong?
You gotta know
That
all.
there's, so no as in like
But
there's no
don't
solution.
you-
There's no solution.
Don't you need
Oh.
to prove that
We can't-
the certificate is wrong?
What do you mean?
So for the verifier, given a certificate, I'll put yes if it's valid for the function, or given a certificate, I'll put no if it's not valid for the function.
Yeah.
So if it's
then,
no,
if it's no, then wouldn't I just do the same thing as a yes instance and just plug it in and see that the function evaluates?
Wait, what do you
0?
mean?
Okay, so let's say I have a yes instance, right?
Yeah,
I plug it
That's
into
what
the
it is.
verifier. Yeah,
Yeah,
right.
okay.
I plug it into the verifier.
That's basically.
Okay, the verifier is going to take my solution, plug it into F, and it's going to equal 1, and so it's going to return yes.
yeah.
Yeah.
Now let's say I give a no instance to the certificate, right?
What do you mean by no instance?
A no instance to
Something
the
that's wrong.
verifier.
So an invalid
Yeah,
instance, like,
invalid instance, yeah.
okay.
So let's say like 0, 0, 0, 0,
Yeah.
right? Then wouldn't the verifier just
Open no.
plug it in into the, it would just be able to plug it in into F and output no, right?
Yeah,
So we can say that that's not the solution.
But then doesn't that mean the verifier knows about yes instances and no instances?
no, the verifier can only tell you that given a certificate,
But didn't you just verify that what Subhakshan said isn't wrong?
or
Just verify that it's wrong.
I'm confused.
no, because I think basically what it was saying.
Yeah, I think basically what it was saying was, so you take the certificate, and the certificate will be here, have your solution, like, we want to know if this certificate is a solution or not, to the problem, right? So we put that into a verifier, and a verifier is gonna tell us, yes, this is a solution, no, this is not a
Yeah,
solution.
with this example that she gave, I think sometime, and she was like, so given two numbers and you're given like a set, like an infinite set, are those two numbers in that infinite set? If they are, then you can easily return yes, because you can find it, but if it's no, then you will never end up like, you will never go like exhausted, you have to go through the whole
Yeah.
set, right? But you'll never stop, so you
Exactly.
can never return a no.
See, that makes
That
sense.
example makes
That-
sense,
that
but
makes
this
sense.
one,
But this one is a bit more trippy, right? Because it's like,
give us.
So we can verify that it is no.
You just plug
is
it
this
in.
MP?
No, yes, this is an empty problem, because, oh wait, okay, let me rephrase that. So if we're given, let's not worry about, right now, let's not worry about whatever outputting, verifier outputting no, okay, just worry about it outputting yes, right? So what this means is that if I claim, for this problem, if I claim that there is a solution, right, then I'll have a certificate, and that certificate can also verify that there is a solution.
Right.
So if I claim that there's a solution, the verifier can back up my claim, given I give it a certificate in polynomial time. But if I claim that there is no solution, right? Even if I have some sort of certificate here, in the no instance, the certificate is a bit vague of what it actually is. But if I claim that the answer is no, there's no way the verifier can actually verify that the answer is no in polynomial time.
Yeah.
So
Right.
you can basically, for this one, you can prove that a specific certificate is false, but you can't prove that there is no solution at all.
Exactly, yeah. Right, I think does that clear up the confusion? Does the verifier can prove a certificate is false
Okay.
or not, but it can't prove that the actual problem is a no, if you give it a no. Or it can be proved in polynomial time, right? So here, what's the only way we can know?
Oh, I see.
What's the only known way we can prove that? If I claim that the answer is no, what's the only way to prove that? Try every combination, right? It's like whenever it's like on the fucking test when they ask you to prove something. If you give a counterexample, you're done right away. If you have to actually prove it, you have to do so much shit. That's kind of what's going down here, right?
What's the, is that a polynomial time decision set?
It's NP.
Yep, like, how
But
do you
you can
verify?
verify it, you can find it basically.
How do you find it?
The example you gave, right?
Because you're gonna
You have two
keep
numbers. No, but as long as you find those two numbers within your set,
Yeah,
but
but
the set
is
is infinite.
but
You
yeah,
will
the
stop.
set is infinite. You go
But
on
you
forever.
won't find it, like.
It will
But
stop.
You will
But
find
let's say
it, but
the
you
set
can
is at the
find
end
it
of
like,
the list.
literally like.
Yeah,
all the
but
way
you
back
find
there.
it, right? Like you will
Yeah.
stop.
You'll never find it because the set is infinite.
Yeah,
But
yeah,
it's a finite number though.
yeah, it's a finite number, but
Oh, but it's
well, how do you represent that in like what's going on? Like what's the
Yeah, it is
representation?
polynomial
It's so
because
n elements.
because
Is that n?
yeah, let's say n is the
Wait, set is n
number of
elements?
in
You
your,
said infinite.
but it's
But
it's
it's
like
not
this,
infinite.
I guess it's
no,
like
no. The
n
set
is the number of
n.
elements.
Oh, and no, n is n is the number.
Yeah.
Oh, it's a
n
set
is the size of the
infinite.
set.
No, no,
The
the
set
set
as
is
n goes
infinite.
to infinity. Okay. If you-
And n is the size of the set, and then n goes to infinity.
Yeah,
Okay.
but your if you're given a certificate,
Yeah.
one verifies the solution, it's gonna take you O of n,
Yeah.
which is polynomial.
Okay.
But
Why
you
would
try
this
every
take
combination
polynomial
plus
to
two to the
solve?
end.
And it's
No, it's not following.
What's that two numbers? What does that verify?
Hmm?
What's
To
the two numbers
verify.
have to do this?
I think
You just plug it in and
add-
see if
That's
it's-
verifying it.
Add and then
Verify.
finish up.
Honestly, no, I think we
Anything
just find
below
those
n
numbers within a set.
Into
Is
the
it like
case,
that?
Things-
so all one.
so you're given a set, you wanna find two numbers in the set that add up to 10.
Something, yeah. And you're given a 10 and those two numbers, and you're just trying to find it within the 10. To find it is all like actually trying
the
to
set is
solve
open?
it. Yeah. 2 to the end.
So you know how I
What's the
just
certificate in
explained,
that case?
Huh?
What's the
The
certificate?
two numbers. Two numbers and its value.
So we just have to add those two numbers and see if it's 10.
You have to find if you have
so
those two
you add
numbers.
the two numbers and you see if it's 10, and then you need to make sure that the two numbers are also in your
Yeah.
set.
Okay.
And that set would be X.
And we'll find it and it's actually going.
It would be But the other thing for it is, we can say, okay, you have O of n, you're going to take O of n and find it in there, right, which is polynomial, but at the same time, it needs to be polynomial in the size of the input, right? So n would be log base 2. So the actual size is equal to log base 2n, which means it's going to take.
No, wait. By his logic, that everything would be exponential in size.
Okay, yo, so let's say you're given a set, right? And you want to find the two numbers in this set that sum up to 10.
Yeah.
Okay? So you claim that there's a verifier that is NP. You claim it's NP, which means that there exists a verifier. Right?
Yeah.
And so you'd say that the verifier can just check for the two numbers. If add the two numbers, if it equals 10, then take the two numbers and search through the set to see if it's inside the set.
Yeah.
Right? And then you verify it.
Yeah.
In order to search through the set, it would take O of n, right? But because we need to consider the size of the input, wouldn't size equal to log base 2 of n? Which would mean it
What do you
would
mean?
have to
No,
Why
be.
would the size be log 2 base n?
So it's like what you're, so if you have O of n, but you actually need to put it in terms of size, right? Like O of something size. So size is equal to log base 2 of n. And if you isolate for n, you can.
See, that's why I don't want to that's why I don't want to
I think-
mention
I
that
think
because it's
if-
too. I still
the thing
don't.
is, if-
I don't really
I
get
think
that. I don't want to.
somewhere
But
that.
if you do
if you're
that,
dealing with
all
a
your
list of numbers,
polynomial.
Yeah, okay, look,
the
look.
size is your
Let's-
limiting factor.
Look, let's guys. Let's ignore that.
Yeah, but if you're dealing with a number like it's prime, it's just one number.
Look,
right?
okay, look. I didn't. To be honest, like I don't really get it. So let's ignore it.
Yeah.
Let's ignore that fact, right? I just wanted to point out that if she ever asks, is prime polynomial, just say no. Is knapsack polynomial, just say no. Other than that, let's forget what I said. I'll probably look into it more and then try to explain it, because I don't fully understand it, right? I think we're just confusing ourselves more in that case, right? But you guys get the verifier now, right?
Yeah.
So basically that means that we can verify that the answer is yes, given the certificate in polynomial time. I think another clearer way that in the slide she said it was that it's in NP if there exists a C such that this V of X will output true in polynomial time. Is that a more clear explanation? That means this problem is in NP if there exists at least one C such that if I plug it into this verifier, it will output true in polynomial time. That's what NP means, right? Okay, now, let's say P versus NP, right? So we know that P is a set of all problems solvable in polynomial time, and P is any problems that can be verified in polynomial time. So we know that at least, we know that P is a subset of NP, right? Why is that?
Because you can
All the
verify them.
polynomials can be verified.
Right, okay, so how do we verify? Say we have a polynomial time algorithm, right? And we have some sort of certificate. How would we verify in polynomial time?
Solve it.
Yeah, you just solve
So
it.
yeah,
and
the
then
complexity is as hard as solving the problem, the original problem.
What do you mean? What do you mean by
So,
solve it?
so, okay, so given a problem, right, okay, given
So
a
let's say,
certificate, right?
Yeah,
Like MST, right?
like,
Given a certificate
yeah.
and,
To do the certificate, you actually need to solve the problem
and then compare.
and then compare it to
Exactly.
that, right?
Exactly.
So worst case scenario, you have to solve the
In
problem.
polynomial
Yeah.
time, right? So you can see that obviously P is an NP, but like if you look at this case, you can't solve the problem in polynomial time. So the only way to verify it is, luckily we can just check, right? But for any problem in P, I mean, there could be a way to check it, but at least in the worst case, we can just solve it and then compare the answers. So P is definitely a subset of NP. So if we, but is NP a subset of P? Well, we don't know, right? Because if it is, then P is equal to NP. So right now, the graph looks like this. P is some sort of subset of NP. We don't know if P is equal to NP. So we know that P is at least some subset, but we don't know if they're equal or not, right? So what is co-NP?
Alex says there you go.
Wrong.
Yo, where's the proof, man?
Groundbreaking.
Wait, so what was the logic again? What was the logic again? So
What, for this?
yeah, so P at least needs
So what's the definition of NP again?
Find the,
that you can verify it in polynomial time.
Right. So if we have a polynomial time algorithm, how can we verify that the answer is right? So if I have a certificate
is in U of T.
and a polynomial and a decision problem that can be solved in polynomial time, how can I verify the certificate?
Tell them how to test this quiz.
Either that's.
Plug in an example solution.
No. So instead of plugging, so let's say for example we have MST, right? Which is given a graph by the minimum spanning tree. What's the certificate going to be? The certificate is going to be a spanning tree, right?
Yeah.
You're trying to prove that if it is the minimum spanning tree,
Mhm.
right? How do we verify that? To verify it, you actually find the minimum spanning tree and compare whatever you found on your algorithm to the actual certificate. If the certificates are equal, if the certificate is equal to the output of your algorithm, then you can verify it, right?
Yeah.
So basically, you were able to verify it in polynomial time because you could actually solve the original problem.
That's worth it.
You
Yeah.
guys get that?
Yeah, yeah.
Serves it.
Okay. Good. So we don't know that NP is in P, and
So what you just say is for P, right? Not NP.
so yeah, so P is a subset of NP.
Yeah. So
Because
you,
any problem that's in P will definitely be verifiable in polynomial time. Okay. What is co-NP? Do you guys know what co-NP is?
Set of all problems with no instances can be verified. Good job.
Right.
That can be.
So, correct? We get a bonus mark on it.
Yes.
Darn.
I think now I'm finally passing the
I'm
midterm.
not gonna write that down, right? Anas, you got that?
What's going to be? Yeah.
Alright, the set of problems whose no instances can be verified in polynomial time.
Who cannot?
Whose no, so if I give you a no, if I tell you the problem is no, I can verify that in polynomial time.
That is not.
That is, the answer is no.
Just
Okay.
literally change that statement and put no instead of yes.
Yes.
Wait, if that's the case, doesn't that mean the problem itself is polynomial time?
No,
You can't say anything about the yes instances, but you know about.
Oh, I see. It's just the
It's
opposite.
the opposite, right?
Oh, wow.
So now, we know,
Does they intersect with co-NP?
Well, that's an example
so we have P, we have N, so we know that NP and co-NP intersect. Does anyone know why?
Why?
Well,
Because anything that's P,
well, we know that P, yeah, I think
co-NP and NP.
so we know that anything that's in P will be in NP, is a subset of NP. Also, anything P will also be a subset of co-NP, right? For the same reason as before, right? If you give me a no answer, I'll just run my polynomial time algorithm and then just compare the solutions. So this intersect, basically, because of these two facts, you know that they intersect, but this NP equal to co-NP?
That,
No.
We don't know.
Wait, what does it mean by P is subset of NP?
So P is a so if a
Subset.
problem is solvable in polynomial time, it is verifiable in polynomial time as well.
Yeah, okay.
Okay.
Wait, if the solution is solvable in polynomial time.
It is verifiable.
Oh, so therefore it's also NP, okay, I see.
It's a subset, yeah, exactly,
Yeah, okay.
exactly.
Yeah,
Same thing here.
that's it.
Alright.
is co-NP intersect NP equal to P?
I think so the whole day.
Not all of it. I remember
Should
she
be,
said
right?
that. No, Dex.
Like, I think the slides.
No.
No,
No, didn't?
No, it's not. In the slide, it's like, yo, selection, the slide is like that.
Yeah, wouldn't it
But we
be-
know that it's guaranteed to intersect. We don't know if, we know it's guaranteed to intersect because of this P, but we know there could be other problems such that they intersect. Okay?
But what are the regions that do not coincide with P but intersect is on the intersect? What does those region
What do you mean
means?
here in this graph?
Yeah, what does those region means? Like,
Probably don't.
So it's, basically that means that it's yes, both it's yes and no instances can be verified in polynomial time, but the actual problem
might not be.
might not be solvable in polynomial time.
Okay. Yeah.
Right? That's what this region means. Yes and no instances can be verified in polynomial time, but we don't know if the problem can actually be
Is
solved.
Sudoku co-NP?
Sudoku is NP.
It is NP, but it's
Obviously,
co-NP.
But why are they not the same? Because NP is solving for yes in
Oh, it
NP
is
time, and then
Is Sudoku co-NP?
Yeah.
yeah.
But
and
because if
solves
Sudoku
for
is
no.
co-NP,
No, it's not.
This one
It can't
is-
be co-NP.
this one's co-NP too,
Why-
right?
Yeah, why?
No, it's not.
It can't
Because
be corn.
if I tell you that the answer is
You
no.
can't verify that there's no.
So if I tell you that there's no solution to Sudoku, how am I going to prove that? I got to try every solution. Right? So if I give you a Sudoku grid, I tell you the answer is
So what's
not.
a co-NP example?
Yeah, exactly.
That's what I got here. They should be.
She didn't provide it in the slides, so.
If Sudoku is co-NP, then this one's co-NP.
No, Sudoku is not
So look at NP.
Wait,
It is not co-NP.
what if the
Wait, why is
the
NP
definition was
not
like
equal?
the no
'Cause
instance?
We don't know.
We don't know.
Like,
They could or not be.
Yeah.
It's not proven whether they're equal or not.
Because you can never tell that there's no solution, given the certificate.
I see.
Okay, let me look at an example
You
of
can prove
co-NP.
that it is a solution, but to prove that there's no solution is not polynomial.
No, but you
So
just
for
wanted.
co-NP would be, you can prove that it's not a solution, but you can't prove that there is a solution.
But you could prove it's not a solution.
Yeah, but you can't prove that there is a solution.
Yeah.
Hence,
But isn't co-NP is that the no instances are verifiable in polynomial time?
yeah, that means to prove that there is a solution, that's Sudoku, that's not gonna be polynomial time.
So
No,
to know
Sudoku
that
is
the
not
one.
co-NP. It's not.
Given a number.
Given a grid,
So
you
he
can't.
has two examples here. Primes. P is a prime number. That's a co-NP.
So
P is a prime number, so if I tell you no.
You can show that a number is not prime because you can find two numbers to multiply it. If I tell you a number is prime, can you ever show that
It is.
it's prime?
Yeah.
Can you ever prove?
No, you're right, you're right. If I tell you the number is not prime,
Yeah.
your certificate will be two numbers that multiply to that number.
Yeah.
So if it's no, the no instance can be verified in polynomial time.
Yeah.
Now if I say the number is prime, what certificate am I going to give you?
Yeah.
You can't, right?
Yeah.
So there you go, that's a good example. So
And
example,
cosat. B is a Boolean expression with no satisfying assignments.
yeah, so it would be the opposite, right?
So yeah, no satisfying assignments.
So SAT is Boolean expression with satisfying assignment. Cosat, and SAT is NP. Right?
Yes.
Cosat is corn.
That's a good example. Is prime one is a good example of co-NP. So if the answer is no, right, that can be verified because you can give two numbers that multiply
Holy
to
fuck.
the number. If I tell you a number is prime, how am I going to prove that? Right? I gotta check all the numbers. That's a good example.
I just looked up co-NP example, and in his lecture on co-NP, yo, holy fuck. Prime,
You guys want pizza?
actually,
No,
primes is in the intersection of NP and
Yo,
co-NP.
you guys want pizza?
never mind there.
This man's a bit.
How? Okay, so if we
Wait, what did he say?
Primes isn't that region the intersection?
What?
Primes.
So if a number is prime, yeah, I tell you the number is prime. No, it can't be. Right, how would you prove it?
Let me actually read it.
If a number's prime, you prove that there's no combination
Exactly.
of
First one to
multiplication.
develop-
Exactly,
That's
exactly.
it.
We first want to develop a different way of determining primality. We want to show that a number p greater than 1 is prime if and only if there is a number r between 1 and p such that r to the power of p minus 1 is equal to 1 mod p.
I think it's a very
No,
complicated.
no, okay, so maybe there is some way, but it's very complicated. Okay, let's just.
Relative
But
primality.
clearly that,
We no one wants
but
pizza.
at least,
No, just open.
at least is prime, it's very
I
obvious
kinda
that it's.
do want pizza, but I
Cohen.
don't want it at the same time. You feel?
Oh, yo, he owes his pizza, right?
Yo, let's all this one after.
You owe us pizza? Why does he owe us pizza?
HQ owes me money.
It's like not there. No, HQ this week. It's 50K.
Oh, it's
What?
But it's winner
Huh?
takes
Yeah, me
all,
too.
that's the thing.
Apparently,
Oh.
we
Because
had
what
a winner
happened
that
last
takes off
week,
50K.
what they started
Last
last
week,
week,
yeah.
every Sunday, that's last man standing or last person, like, yeah, right?
This
So
guy,
if-
this guy. you
So
couldn't
in
catch
the
that?
end, if everyone
Could you cash that
fails,
in?
no one gets the money. So since they didn't give it out last week, this week it's 50K, but it's the same thing. Last person standing. So if there's two people and both of them fill a question, no one gets the money. And then that money gets pushed to next week too. Oh, 50K. 1K. In 59, no. Like, that can just be a life goal, you know? Like every week, just hustle hard and get it. You don't need to work the whole year. Literally.
What room number is this? 119.
Yeah.
This man's ordering pizza. Alright, we're not even done the first lecture, and this lecture, I don't think will be relevant to the quiz, so.
Or good basic idea.
Oh, tomorrow at 9 a.m. there's a circus lecture.
Oh.
9 a.m. circus lecture.
I'm not going, fuck that.
Wait, for what?